Welcome to this video lesson which focuses on the distance of a point to a plane. Some of the knowledge that you need to have prior to watching this video is the introduction to planes, cross products, and dot products. To figure out the shortest distance from a plane to a point, we have to draw a plane and we need a point. We're going to use variables x, y, z for the coordinates of this point. And we're going to imagine that we have one point on the plane and we have the normal to the plane as well. So for example, if you were given the Cartesian form of the line. Note that the shortest distance from point P to the plane will also be a perpendicular line to it. So that's parallel to the normal. And the point at which it meets the plane is going to be called foot of the normal to the plane. We're going to draw a line that connects Q to P, and we're also going to draw a line which is parallel to the plane, and that's going to intersect the normal, and the shortest distance is going to be from that intersection to the plane, and we're going to label angle theta the angle between the line and the normal. And the triangle that we have formed is a right angle triangle, and D is equal to the magnitude of the hypotenuse, which is the magnitude of vector QP multiplied by cosine of theta. Now the dot product of vector QP and the normal is going to be the magnitude of QP times the magnitude of the normal times cosine of theta. We will rearrange this for the acute angle, putting the absolute values. And we are going to replace cosine of theta by this new expression in our equation. The magnitude of vector QP is both on the numerator and the denominator, so it cancels out, leaving us with the expression of the dot product of QP and the normal divided by the magnitude of the normal for our shortest distance. We have all the components of QP and vector n, and if we put them together, we will get the magnitude of ax plus by plus cz plus d over the magnitude of the normal is going to be the x component squared plus the y component squared plus the z component squared, and that's a squared plus b squared plus c squared rooted. And here the d value is negative ax naught minus by naught minus cz naught. And that's the expression that we can use to find the shortest distance from a point to a plane. Let's look at the foot of the normal now. The foot of the normal is where the point meets the plane at the shortest distance. So in this example, we want to determine the foot of the normal from point 102 to the plane that's given. Let's draw out this situation to get a visual view of what it looks like. We need a plane, we need a normal, we need a point P with coordinates 102, and we need the foot of the normal, let's call it Q, with coordinates x, y, z. Now we can determine the normal components from the Cartesian form. In this case, the coefficients of our x, y, z are 2, 1, and negative 2. And the parametric equation of QP will have point P. For x component, the point is 1, and the direction comes from the normal, that's 2t. Y component is 0, and the normal of that is 1t. And the z component has a point value or a z value of 2, and the normal component in the z direction of negative 2, giving us 2 minus 2t. Now we have the equation of line that goes through P and Q, and we know that point Q is on that line, and it's also on the plane 2x plus y minus 2z plus 11 is equal to 0. So we can use that idea, we can plug in all the parametric equation values for x, y, z into the plane equation for x, y, z. And once we do that, we can expand and simplify and solve for our t value. In this case, we will have 4t plus t, which is 9t, and we will have 2 minus 4 plus 11, which is 9. Bringing that to the right hand side, we get negative 9, and we will get t is equal to negative 1. Once we have this t-value, we can plug it back into the parametric equation and we will get the exact coordinates of point Q, or the foot of the normal. And this is where line PQ meets the plane at the shortest distance. Our final value for the coordinates are -1, -1, 4 for the x, y, and the z coordinates of the point. The summary of the concepts of this video is fast forwarded here, so if you want to pause the video and write any of the information, please feel free to do so. And now we are going to look at an example. In this example, we are going to determine the shortest distance between point P321 and the plane that's given to us. In order to use the equation that we have obtained, we need the Cartesian form of the equation, and we need the normal. So we do have the two vectors that are parallel to our plane, vectors b and c, but we need to find a normal, and we do that by the cross product. The cross product here will be, for the x component, we will multiply 1 by -1 and subtract it by 1 times 1. For the negative y component, we will multiply 2 and -1 and subtract it by 2 times 1. And for the positive z component, we are going to multiply 2 and 1 and subtract it by 1 times 2. By doing this, we will end up getting components -2, 4, and 0 for our x, y, z. And since this is a direction vector or normal vector, we can simplify it or divide it by 2 to get 1, -2, 0. We can choose any of these two to write our equation. It doesn't really make a difference, so let's try the -2, 4, and 0. In this case, we will get -2 times x plus 4 times y plus 0 times z plus d is equal to 0. We're going to use our point that is on the plane. This is 3, 1, 2. So we will get -2 times 3 plus 4 times 1 times 0 times 2 plus d is equal to 0. And we will solve for d to get 2. Meaning that our equation, our Cartesian form, is going to be -2x plus 4y plus 2 is equal to 0. Now, to find the shortest distance, since we already have the Cartesian form of the equation, we can either find the foot of the perpendicular to the plane first and then use that to find the vector and then its magnitude, or we can just use the equation. In this case, we're going to use the equation, and we are going to use the point 321 because we want to see the shortest distance from that point to the plane. And we're going to plug those values in for x, y, and z into our Cartesian form of the equation, and we are going to find the magnitude of our normal vector there, and that's going to be -2 squared plus 4 squared. Once we do all the calculation and we simplify our answer, we get 2 over root 5 or 2 root 5 over 5 in a simplified rational form. I have prepared 2 questions for you folks to try out on your own, and I will try to post the full solution to these as soon as I can in a separate video. I hope that this video was helpful in giving you an idea about how we can find the distance from a point to a plane, or the shortest distance, or how we can find the foot of the perpendicular to the plane. Thank you for watching.